Okay, right. KS4 waves, part 5. Rattling through these now. So, I'm not going to go back over all the things that we've done. Apart from last week. Last week we were looking at seismic waves. This week we are looking at the electromagnetic spectrum. Again, this is lesson 5. If you're just jumping in here and you're not quite sure about amplitude, wavelength, frequency, speed, things like this, you need to go back and have a look at the others. But yeah, right, electromagnetic spectrum. So, what is the electromagnetic spectrum? Well, starting off here, we've got our picture of an eye. So obviously this is something to do with what we can see, visual light. Now, the visible spectrum of light that we can see is a very, very small part of what we call the electromagnetic spectrum. Okay, so I'm sure most of you would have seen or come across the idea of what this picture is about. Some of you you'll think Pink Floyd, Dark Side of the Moon, really, really good album by the way. Others of you, you'll know that this is dispersion, which we'll come across into a later point, which is also light refraction through a prism, which results in dispersion of white light. So white light itself is what we call the visible light, okay, which is a small part of the electromagnetic spectrum. But inside white light, we have this range of wavelengths of light as well, which go from, which is basically how we see a rainbow. Rainbows are basically where white light has been split into these different wavelengths as it's gone through a water drop. So you get from red all the way through to indigo, violet and indigo. So basically the way that it is that the shorter the wavelength, the more that it's actually refracted as it goes through the prism. So as you can tell here, is that our violets and our indigos, right down the bottom here, are shorter wavelengths. So they're shorter wavelengths, but they'll be higher frequency. Whereas our reds are a longer wavelength, so therefore they've been bent less, or they've been refracted less as they've gone through this prism. Don't worry too much about these terms, refraction, diffraction and dispersion. We're going to come on to those in our later lessons, but just to get the idea that white light, as it goes through a prism, the light is bent, and depending on the different wavelengths of the light that makes up that white light will depend on how much they are bent, and obviously at what lines these different colours of white light actually come out. So, as you're saying, electromagnetic spectrum. Visible light, as we see here, is a small, sort of middle-ish section of the electromagnetic spectrum. So, all the electromagnetic spectrum, it doesn't need a medium of which it to travel through, because what it actually does is that it's a transverse wave, but also at the moment that we have a transverse wave, we actually have a wave that travels, so if we imagine that we've got our wave, our transverse wave going like this, what you actually need to imagine as well is that along this centre line, there's another transverse wave that if I was to draw it would be coming in and out of the board, okay? So it's a bit like a cross. So our vertical one is our actual light wave, and what's actually travelling this side is our electric and magnetic field that this is actually travelling on. Now, because it's travelling on that means it doesn't actually need a medium to travel through. Unlike our sound waves and our our longitudinal waves that must have a medium to travel through, these don't need that. So the good thing about that is that means that they can travel in a vacuum, which means that they can travel in space, and through a vacuum, all of these will travel at the same speed through a vacuum. As we said on the speed of sound, we know the speed of sound is 340 meters per second. And if you watched the previous lessons, you'd also know the answer to how fast the speed of light is. Anyone? Well, if you don't remember, it's roughly 300 million meters per second, which is it's an outrageous speed, absolutely outrageous speed. So our electromagnetic spectrum here, we've got different lengths or different wavelengths. So the shorter wavelengths, generally means higher frequency. So shorter wavelengths, so right at the top here we've got gamma radiation and X-rays. Obviously we know X-rays, they get used in medicine, have a look on your insides. Gamma rays, these are actually used in medicine as well. They're good for, they're used for killing cancer cells. Then we come down into the sort of The shorter side of visible light, or going above visible light even, is our ultraviolet lights. Then we get to our visible light section, and then we get to our infrareds, microwaves, and radio waves. So, infrareds, we know infrared radiation, which can come from heat sources, can come from the sun. Ultraviolet, which also comes from the sun as well. Microwaves, we know in your microwaves, surprisingly enough, that's why they're called microwaves. And radio waves, for those of you that still listen to radio and not through the internet and not through digital signals, these are through analog radio waves. Okay, so this is our electromagnetic spectrum. As you can see, there's many uses, loads of different uses for all of the different wavelengths and all the different types of waves during the electromagnetic spectrum. So here we've got right up here with our short wavelengths, our gamma rays and our X-rays. So these are roughly, along the same, on a scale, about the size in comparison to a radio wave being the size of a building. Our gamma ray would be the size of an atomic nucleus. So a massive difference in size of those wavelengths. Obviously, so we look at our frequencies again. Small wavelengths result in a high frequency, with our longer wavelengths resulting in a lower frequency. So obviously the temperatures that can be produced from these different types of wavelengths. So again, the shorter the wavelength, the higher the frequency, the higher the resulting temperature when it interacts with something. Okay? So, the dangers of the electromagnetic spectrum. So as we were talking about just the slide before, high temperatures can be produced from these smaller wavelengths, higher end frequencies of these electromagnetic spectrum. So I mean, starting off, microwaves, we know what microwaves do. You have 9 times out of 10 you've got a microwave in your kitchen. What do? You put food in it, you press the button, it heats up the water molecules, and that itself then obviously produces heat. It can do exactly the same in high densities or high quantities to the cells in the body. It will start to heat you from the outside, so generally not really good for your cells. It will heat them up, it will denature them. Really bad news. Infrared radiation comes from the sun. We feel it as heat. Again, in too higher quantities, it will start to burn the top layers of your skin, which if you ever had sunburn, you know it's bad news. And if you ever had heat stroke, like when you get burnt across your chest or your forehead, it can make you feel really ill. So again, generally not good news. X-rays and gamma rays, now these produce a massive amount of heat and actually have the ability to mutate your cells. So not in like a really cool X-Men kind of way, wicked, I'm going to be Wolverine. Unfortunately it's not that good. Really is not that good. If you start mutating your cells, the cells will generally die. Again, really bad news. And then this leads on to my final point. The final point of electromagnetic spectrum I want to look at is UV. So obviously we've got a young lady here in a sunbed. She's trying to soak up those rays. Now you would think that the suntan is from your skin getting cooked or getting really heated up from the sun. What actually your suntan is actually your body trying to protect yourself. Now UV rays can actually be quite dangerous to the body. So what the body actually does as a defence mechanism is it makes the top layer of your skin go dark. And now the reason for this is that a darker skin absorbs the UV rays better, which means that the UV rays can't reach the lower levels of the skin where it can create more damage. And the reason for this is that there's 3 main types of UV. There's UVA, which is a low frequency. This is weaker effects than UVB. So UVB has a medium frequency, and this can cause severe sunburn and obviously damage to the skin cells. And then top of the range, UVC, which is obviously high frequency, and this can cause severe damage to the skin cells. So this is how your body tries to protect you. It tries to go as dark as possible to prevent these UV rays getting to the lower levels of your skin and damaging those skin cells for future growth. So just remember that next time you're out in the sun and you're not, especially for the, those girls and guys that are really pale skinned, you go red, those UV rays are really going to start harming you. So it's always about the sunblock. Even if you're not that pale, I love the sun, but get that sunblock on. It's going to be good for you. It's going to stop your skin getting damaged, okay? And it's obviously going to reduce the levels of getting skin cancer as well. So our overview was a general look at the electromagnetic spectrum, a bit of a tornado sort of run through it. Obviously looking at the different properties across the spectrum, how the different levels of the spectrum actually work and what they're used for, and obviously we had a look at the dangers of some of those sections of the electromagnetic spectrum as well. So that's the end of today's lesson. Next lesson we're actually going to be looking at reflection and refraction of waves. So my name's Ian McDowell, I'm a student at University. Cheers.